morning. Yesterday we explained some of the significance of the components of the hydraulic conductivity or the gradient as well as the velocity. We'll also expatiate more on that when we will talk about transmissivity, because there we will realize the significance of the vertical component of the hydraulic conductivity, okay, and what transmissivity really stands for. Today we will briefly look at how do we determine the hydraulic conductivity, okay? How do we determine hydraulic conductivity? No, hydraulic gradient, not conductivity, hydraulic gradient. In this case, we will take something called the three-point problem. The three-point problem is a method of determining the direction of the velocity of groundwater flow. So in essence, it gives us the flow direction. Okay? In essence, it gives us the flow direction. How do we go about the three-point problem? Here we will be considering the horizontal component of field applications, and then it will be represented as a single vector perpendicular to flow lines. By flow lines here, we mean equipotential surface. Equipotential surface. Equipotential surface. And equipotential surface, as the name implies, is just like a contour on which you have the pressure head to be the same at every point on the contour. Not the same way as you have contours for elevation, isn't it? For elevation contours, at every point on the contour, the elevation is the same. The same thing with equipotential surface. At every point on the contour, the piezometric head, in this case, which is the pressure head, isn't it? So at every point on the contour, the piezometric head or the pressure head is the same. Okay? So, pardon? What?
Smooth surface.
No.
Where there's no, the contour is just smooth straight.
No, I'm not referring to elevation contours. I just made reference to elevation contours to explain the fact that at every point on the contour, the elevation for the elevation contour is the same. For equipotential surface or contours, at every point on the contour, the pressure head or piezometric head is the same. Do you get the point? It's just like when you have, let's say this is your ground surface, this is your ground surface, and then probably when you sink your wells, observation wells, okay, or test wells, and the pressure head here is the same as the pressure head here. So you can have some lines, okay, depending on the piezometers. By piezometers, we mean some test wells that penetrate the aquifer or the unconfined aquifer to give the level of the water table or the piezometric head or the phreatic surface. By the way, what is the relationship between piezometric head, pressure, okay, piezometric head, phreatic surface, and water table?
Water table is for unconfined aquifer, the level of water.
Okay.
Unconfined aquifer, the piezometric surface and the phreatic surface is for the confined water level.
It's for the confined aquifer. Then, is there anything in common between these two?
Water level.
Is there anything in common between among these three? Anything in common?
Water
Yes.
level in the aquifers.
What?
In the case of the volumetric surface, just like an imaginary line that depicts the
That what?
in a confined that depicts the level of water in a confined aquifer.
Okay, for the piezometric surface. What about the phreatic surface? Phreatic surface. Phreatic surface. What about that one? These are simple terminologies, but believe you me, you really need to understand them very well, as simple as they may seem. What about phreatic surface? Surface.
Should it be the level of water that will stand in a piezometer?
So is it equal to the water table?
Sir?
Is it the same thing as the water table?
Yes, but for the confined case.
Is it necessarily for confined case for the phreatic surface? Is it necessarily for the confined aquifer?
Confined is piezometric surface.
Okay, I accept that. Now water table, he said for unconfined, then phreatic surface.
So that has to do with
Hmm?
artisan well, proof
What? Talk.
I think it has to do with artisan well.
What? The phreatic surface?
Artisan well, yeah.
Yeah, the phreatic surface can also be considered as water table, can be called water table. But then there could be certain instances that they may not be the same. Okay? There are certain instances that they may not be the same. The phreatic surface is the surface, when you dig, let's say, a piezometer, a test well, the level of water in the well. But then, the water table could be somewhere like this. Okay? Of course, more often than not, if you have abstraction, you have cone of depression. But sometimes, even if you don't have any abstraction, you just dig your test well, the saturated level of the water table is usually above the level of water in the well. Are you getting the point? Why is that so?
I think
More often than not, this is the water table. But when you dig a well, instead of the level inside the well to be the same as the water table, isn't it? You have depression down. What? The aquifer is not. What do you mean by the aquifer is not under pressure? How does that explain this?
Unconfined because there are no two impermeable layers in between the aquifer.
What?
Two impermeable layers in between the aquifer.
No, here we are talking about the unconfined aquifer. Here we are talking about the unconfined aquifer.
That's what I'm saying, sir.
Okay.
If it is open at the top, it means the water will reach the level of the water table.
Why?
Because it's not under pressure.
What?
It's not under pressure.
It's not under pressure. When you have a bowl, a bucket here, then you have a tube. In fact, it may even rise above, right? Due to capillary, depending on the size of the bowl. If the size is so small, you have capillary rise. Am I right? If it is so big, then the minimum you have is that it will be at the same level as the water in the bowl. Am I right? So, why do we have a different case here? What?
Losses.
What do you mean by losses?
The scale of the wave is water.
The what?
The scale
The screen?
of the water
Okay.
is located at the bottom.
Okay.
So the process of the water to go down and rise up ultimately will that's always.
When we're explaining the types of aquifers, when we're explaining the classification of aquifers in terms of the presence of impervious layer above or beneath, we explained so deeply into the hydraulics and the behavior, both in the confined and unconfined aquifer, right? What did we say about the pressure? The pressure. What's the pressure here?
The pressure normally will be below the atmosphere.
The pressure here at this point. What is the pressure? Do you accept? Do you accept? Okay, what is your own view? The pressure on the surface of the water inside the well is lower than atmospheric? Are you looking at the point? Look at the location here on the surface of the water in the well. What is the pressure? Atmospheric. Okay. Yeah. The pressure is atmospheric. Now, what is the pressure in the unsaturated zone, in the vadose zone? What is the pressure in the vadose zone? Vadose zone. Vadose. What do you mean by hydrostatic pressure? This we explained. I took a lot of time explaining all this. That was probably even my second class or even first class. I don't remember. Maybe my first or second class. I took a lot of time explaining all these things.
It's going to be the pressure and the atmospheric pressure.
Yes. You have the slides. So this one, there is no excuse that I don't have the slide. Although the slide is just the profile. You know, you have the confined, unconfined, but all the explanation is not in the slide. I mean, no explanation was on the slide apart from the figure. So I just used the figure to explain the different regimes. What?
Negative atmospheric pressure.
Negative.
Assumption
Tension. It's under tension, right? Only one person bailed you out, but it means maybe all the remaining couldn't remember exactly what it is. And these are, the basis. Whether hydrology, whether groundwater modeling, whatever it is, they help you understanding the process completely. Because if you don't get this right, you cannot move further. And there is the reason why I'm asking this question, which is where we are going to now. In the unsaturated zone, you have the pressure to be under tension, which is negative, below the atmospheric pressure. If you remember, that was why I took my time to explain all the different pressures that we have. The different pressures that we have. The gauge pressure, the atmospheric, the vacuum, and all that stuff. Now, there is a transition zone between the unsaturated and the saturated zone, right? Am I right? There is a transition zone. What do you call that transition zone? Between the unsaturated and the saturated zone. There is a transition zone.
Yes.
And what do we call that?
Capillary fringe.
Capillary fringe. Good. You see, I know if I will ask all of you, some of you may not remember this. Am I right? I cannot emphasize the need for you to, one, to take what you do serious. Two, to be able to remember basic aspects to do with the groundwater. Because I'm sure if I will give you an exam now to tell me this transition zone, some will pass, of course, but probably a lot will fail, which is not supposed to be, because we discussed this at length. And even before this time, we know you must have done groundwater hydrology before, and you must have treated that. But that is by the way. Now, the capillary fringe is the transition zone. Another question. Who do I ask this time around? Or do I ask for a volunteer? What is the pressure in the capillary fringe? Let me ask for a volunteer now. What is the pressure in the capillary fringe? No volunteer? If nobody volunteers, it means I will have to force someone to volunteer.
Almost equals to the atmospheric pressure.
Now, what do you mean by almost equals to the atmospheric pressure?
It is.
You have to be specific.
This.
Because I use transition, so you want to also put it like transition between this? No, that is not acceptable. You have to be specific. Yes, you want to help me out?
It is the capillary pressure.
What?
Capillary pressure.
Capillary pressure. What did we define capillary pressure? Can you remember? What did you define capillary pressure?
The difference between atmospheric, you define it as atmospheric pressure minus water pressure.
Okay, now, can you tell me the pressure of the capillary fringe with respect to the atmospheric pressure?
Sir?
Can you tell me the pressure of the capillary fringe with respect to the atmospheric pressure?
Then you say the pressure.
Okay, anybody volunteer? Anybody?
It's the same as atmospheric pressure.
It's equal to the atmospheric pressure.
It's equal to?
The atmospheric pressure.
It's equal to atmospheric pressure. No, it is not.
Water pressure.
It is under suction. Because if you remember, what did we say about the capillary fringe? That it is almost saturated. Almost saturated. Yet, water is still not available
For transmission.
to wells. It is not available to wells. The water in the capillary fringe is not available to wells. Because still, although it is almost saturated, but the water is tightly held against gravity by the capillary forces, surface tension, and what have you. So it's not available to wells. Although it is almost saturated, but the pressure is below atmospheric. For that reason, you have the level in the well to be lower. Although the water table could represent the capillary fringe, because I said it's almost saturated, isn't it? But when we go deeper, when you dig a well, instead of the level to be the same as the level of the water table, no, because of the capillary fringe. And you can calculate this height because it is dependent upon the size of the pores and the grains, because that will determine the capillary rise. Okay? So, these are some technical things that you need to know. Okay? And part of the reasons, as he mentioned, is you are using your phone. And part of the reasons could be the entry losses. Okay? But the main thing is that what I want to emphasize is that water table could coincide with the phreatic surface. And sometimes it may not. So bear that in mind. And that could be due to the capillary fringe. Because water is almost saturated, yet not available. And the pressure in the capillary fringe is not atmospheric. It is under suction. Same as the pressure in the unsaturated zone. It's under tension. Negative pressure. That is below atmospheric pressure. Now let me ask you this simple question. I know this one, all of you will get this. In the well, what is the pressure at this point? Yes, our. In the well, inside the well, what is the pressure at this point A? What? You don't? You were here during my first and second classes, right? Oh. What about you? You were not here. Did you listen to our audio recording? Pardon? Why? Is he not a part of the WhatsApp group? Part of the significance of recording is for the benefit of one, probably for one reason or the other, those that may be absent. Two, for you to revise, because like I mentioned, my slides are not satisfactory, unfortunately, and that's how it should be. It is not a flow, but that is how it should be. PowerPoint slides are supposed to guide you, not that you will populate it with everything, just like you do when presenting. Most of you, some of you, when doing presentation, for your thesis, you populate with lots of text and what have you. While it's supposed you just have some bulleted points, and then you expatiate on that. So my PowerPoint, unfortunately, I only have some few points. But then on one slide, probably I can spend 2 hours explaining it. So you can just imagine if I were to put everything down, how many slides are we going to have? So the significance of the audio is for you to revise, and then if for any reason you miss the class, you will just miss it probably physically, but then you have the slide, you have the audio recording which you can follow. And then at the end, you will only lose something very little. And this is the basics, the very fundamental. What about it?
The pressure at that point is equal to the sum of the pressure of the column of water above the quantity plus atmospheric pressure.
Plus atmospheric pressure? Someone, you are all using your phones in the class. Oh.
He's checking the slide.
He's checking?
The slide.
Which slide?
On this topic.
What?
On this topic, the one that.
Oh, fortunately you won't find anything. I told you now. I told you. All you will see is one diagram which has, unconfined, aquifer, and confined. And probably on that diagram, I spent 1 hour explaining it. That's all you can see. You cannot find anything in the slide. Only the figure. So, do you accept what he said? No, just look at it here. Point A. I'm asking for the pressure here. Can you tell me?
From what he said, I think it technically is correct.
What did he say?
He said the summation of the atmospheric pressure plus the total air.
Okay. All right.
Please, you said there is condition for the free thick surface to coincide with the water table.
More often than not, they don't coincide. The phreatic surface is the level of water in the piezometer. Then this is the water table. And the water table, more often than not, includes the level is usually, because the capillary fringe is so small, the height of the capillary fringe is depending on the grain size. If the grain size is like in clay, which is an aquifer, it could be higher. But for aquifers, because aquifers mean they conduct, isn't it? It has a reasonable amount of interconnected pores. So the height of the capillary fringe is so small. And more often than not, it is undifferentiable with the water with the what do I call the phreatic surface. Like when you come here, the phreatic surface will be something imaginary, not physical. It will be something like imaginary, something like below the water table. Do you understand? Below the water table. Like an imaginary line. Taking care of the capillary fringe. Because above it is the capillary fringe. This would play greater role when we'll be talking about the flow in unsaturated zone, which due to time factor, we may not consider that in detail. The flow in unsaturated zone. And that has a lot of impact when you are discussing about remediation. When you have oil spill, it moves through the unsaturated zone. What happens when you dig a well and then you test the water and it smells kerosene or hydrocarbon? How do you determine the quantity or the amount of the contaminant within that aquifer? Because you just dig a well and then probably the level that is about, maybe let's say 0.5 centimeter thickness of the hydrocarbon in your test well. So how do you now calculate the amount or the volume of that hydrocarbon within that aquifer based on the level or the depth of the amount or of the hydrocarbon within the well? So that will now take us into the knowledge of the flow in unsaturated zone. And all these aspects of capillary fringe and water table will now come into play very well. But like I mentioned, we will not go deep into that, but just so you know, okay? Just so you know that it plays important role. The phreatic surface is usually imaginary because it is the surface where the pressure head, the atmospheric pressure is 0. And then you have capillary fringe above it. Okay? Yes.
You said the water in the capillary fringe is almost saturated, means that about to saturate it.
Yes.
To why that the water is not available to aquifer?
It's not available because it is held by capillary forces. It is tightly held.
They will not allow it to.
Yes, it is tightly held. It is tightly held to the aquifer grains, to the porous media, okay, to the aquifer skeleton. It is tightly held. Okay? All right. So, back to the determination of the velocity or the hydraulic gradient. I was just explaining piezometric surface, isn't it? That's what took us to water table, to phreatic surface, which is a very important concept that needs clarification. Now, here we have three wells, H1, H2, H3. These values are the piezometric heads in the wells. And the piezometric heads, how do you determine it? The elevation of the surface minus the depth to the surface of the water, isn't it? This is like in practice, isn't it? You have your GPS here, you take the elevation, the surface elevation, isn't it? The surface elevation here, isn't it? Let's say it's 500. What's the elevation of Abu or Zaria above mean sea level? 600 plus, right? So let's say about 600 meters. Okay? And then when you sink your piezometer, or when you measure the depth from this level to the top of the water, let's say it is 3 meters. So what is the pressure head or the piezometric head? It will be 600 minus 3, right? Which is 597, right? So this is the head, isn't it? So that is how these heads are determined. Are you following? Are you following? Now, from here, you see, it means the groundwater, of course, it will move from higher pressure, from points of lower pressure head to points of higher pressure head. Ah, my friend is sleeping. I saw you. Is that okay? But you have to open your eyes, and so that I know that you are not just listening but looking at the board. Okay? So it moves from lower pressure to higher? Higher to lower, isn't it? So in that case, we will expect movement, because this is 286.11, 284.87, 282.68. So something like, if you move this way, the pressure head is reducing. Here I'm not talking about elevation, but pressure head. Mark my words, pressure head. Okay? And then when you move up, the pressure head is increasing. So water will be expected to flow from higher pressure point of pressure head to points of lower pressure head, isn't it? So what do we do here? We try to now construct some imaginary contours, some imaginary points of equal pressure heads based on these three values. Okay? And contours are usually, instead of using 286.11, we usually take whole numbers, isn't it? So from here, 286, 284. So 286 will lie above this, isn't it? And then you have another one, 284, this one. Okay? Which is above this. And then you have 282. Of course, sometimes they may not necessarily be straight lines. Okay, because these are imaginary lines. It means at every point on this line, the pressure head is 286. And this is practically possible, isn't it? It is practically possible. Because, no, this is the ground surface. Let's say you see, this is the water table. Okay? So if you take lateral lines, segments, some width across, it will be point of equal, because this way it is decreasing, but laterally, perpendicular to this, it will have equal, isn't it? Are you following? All right. So when we have these lines, then flow is represented as a single vector perpendicular to flow lines. These are the flow lines. It has to be perpendicular to flow lines because it has direction, isn't it? Up will be what? Hydraulic gradient? Up. Up from 282 to 286, increasing towards the direction of increasing pressure head. Not hydraulic gradient? Gradient, right? Okay, so because we are moving towards the direction of the greatest rate of increase in the pressure head, isn't it? So this way we have gradient, isn't it? Del H by del S, or the delta H by delta S, because we are considering a horizontal plane. That's why we are using the S. Okay? And it has to be perpendicular to the flow line or the equipotential surface. It has to be perpendicular, meaning this angle is 90 degrees. Now, if this is the gradient, what about the hydraulic gradient? Opposite, isn't it? Which is towards the direction of decreasing head. 286, 282, isn't it? This way. What about the velocity? The same direction, isn't it? Because the velocity direction indicates the flow direction as well, isn't it? Are you following? So now pictorially we can say, okay, we can determine the gradient, isn't it? By taking any two successive lines, isn't it? Here we are given the distance between 286 and 282, which is 385. And the pressure head drop is 4, because 286 minus 282. Am I right? So the hydraulic gradient, or the gradient in this case, is now going to be this amount. Although this is the hydraulic gradient, because if you take this minus that, is going to be negative, isn't it? And the hydraulic gradient is negative of the gradient, okay? So this gives the hydraulic gradient. Are we following? Which is just simply dividing delta H by delta S. Yes.
How do we get delta X?
S is given from the problem. Delta S.
Okay, it's given.
Yeah, it's given. It's just something that you can look from the figure and probably determine it. But this one, you also determine from the difference in the piezometric heads.
So delta S means what? Distance between
The surface distance between the contours.
surface distance.
Yeah, surface distance. Yeah. Because this is like a plan, isn't it? It's like a plan. Okay?
When out of the quantum, you can take any point.
Yes. If you have the distance between, let's say, 282 and 284, you can do that, and you'll arrive at the same answer. Okay? So this is the horizontal component for field application. The vertical component, often taken as positive downward. That's for the hydraulic gradient. Often taken as positive downward. Why is it taken as positive downward? If you see in this case, because we are dealing with vectors, any vector quantity we are mentioning, we have to be specific about the direction, isn't it? Because we are now no longer just treating them as physical quantities. No. If it's a scalar, then we will not be bothered about anything called direction. But if it's a vector quantity, no. We have to be specific about the direction. Okay? Yes. Why do we say that? Often taken as positive downward for the vertical component. If you remember the hydraulic gradient, you see it has a vertical component, right? And horizontal component. So this is what we determine, the resultant horizontal component. And then we say the vertical component of the hydraulic gradient is often taken as positive downward. Why is it taken as positive downward? The answer is right there. You just look at the figure and then tell me.
Because it's the greatest decrease of.
Go ahead. Is the greatest decrease in head?
Decrease.
Okay. Or because it flows down, isn't it? What about the direction of the velocity? It goes down, isn't it? So the direction of the hydraulic gradient is in the same direction as that of the velocity. Okay? It's going down. So, but the gradient goes up. Am I right? So for this figure, we have two wells. These are the heads in the two wells. So delta H is the difference in the heads, and then this is the difference in elevation. Okay? So to get the hydraulic gradient, we divide delta H by delta Z. Okay? But then, can we have a situation whereby the flow direction, because here we are saying that the direction of flow of water is vertical, not only vertical but downward, isn't it? So can we have the opposite, in which water probably will flow upward? But what will be the condition? I mean, why will that happen? How could that happen? What? Okay, I even have, let's say I have, these are aquitars. Okay, this is the water table. This unconfined aquifer and this confined aquifer. And as we're going to see on boundary condition, you have something called probably sometimes leaky aquifers. You may have some, when we're discussing about vertical flow, we said there could be flow between adjacent aquifers, isn't it? Due to, most especially at the points where you have sources or sinks, when you have a well. Although this we are also going to explain in detail when we come to explain the transmissivity. But you can have flow upward. From the unconfined to the confined. Sorry, from the confined to the unconfined. Who can now briefly and specifically tell me why will that happen?
He said that because confined aquifer is the water is under pressure.
Okay.
That is why there is flow vertically upward.
Flow vertically? Did I mention this? Did I mention this? It seems you are the only guy who had that. It seems you are the only person who had it from me.
So the flow is above atmospheric pressure. Inside the confined aquifer, the boundary automatically is above the atmospheric pressure. That's why it's going to rise up against it.
but you have, overburden, huge amount of water on top of it. Okay, we will have an assignment. Don't worry, we will have an assignment. But I think after this, we will have our first assignment. So, and all this explanation I did during my first lecture. I think it was the first lecture, right? When I was explaining the classification of aquifers based on the presence of impervious layer, where we have something like this, and then we spend a lot of time talking about the regions, the confined, the unconfined. No, don't worry. No. I want it written. I want it in writing now. Don't worry. I will have it in writing. Okay. But the answer, is already. I have already discussed it extensively. But why am I saying this? Because, like here, we're assuming the flow is, but we shouldn't be myopic and think all the time that the flow is only downward. That is why I brought this issue. That you can have an upward flow. Although here is saturated, yet you have an upward flow. But then I wanted you to explain to me, using your knowledge of the background, the knowledge of the properties of the confined aquifer and the unconfined aquifer. But you have started giving some points. So we will see that in the assignment. Okay, it's going to be issued today. Okay, I'm going to post it right after this class. Okay, so just take your time and then think about why will that, and then give convincing answers. Okay, and when you copy from someone, I will get you. It means the copier, the original X. Yeah. The copier, the original X. Yes.
I just want to make an analogy. I don't know. Is it the same thing like when you have your well drinking?
No, now I'm not discussing that one. I'm not discussing it anymore. Because you mentioned that you were not in my first two classes or first class. So now probably you may need to go back and listen and understand exactly what I said during the first class. But it's very simple. It's very simple. Don't worry. It's very simple. But I don't overlook simple questions. I have to make sure that no matter how simple it is understood by everyone. Because once your foundation is not good, you cannot build anything solid on that. Okay? But it's very simple and straightforward. And then, this is the homework number 1. Although I will add another question to this one, okay? Here it says you have given the following observations of the piezometric heads. Although those auditing the course will not participate in this homework. Okay? Yeah, they are exempted. Those auditing the course, they are exempted from participating in this homework. Given the following observations of the piezometric heads in 3 observation wells. Well, A, B, C, these are the coordinates and these are the piezometric heads. Assume that the wells penetrate a homogeneous, isotropic, confined aquifer of constant thickness, B equal 20 meter, porosity equal 0.2, and hydraulic conductivity 15 meter per day. And that the piezometric surface between the wells can be approximated as a plane. Determine A, the hydraulic gradient, the magnitude and direction, the total discharge in the aquifer per unit width, and the velocity of the water at a point P, whose coordinates are 100 meter and 100 meter. Okay? So this assignment is to be submitted next week during the class time, okay? Just 1 week. Although, like I said, I will add another question to it. So I will add it and then send to the group. Okay? Now, let's move on. What are you saying? What are you saying?
No.
What are you saying?
No, he asked. He said, "Is it the same question he gave us?" I said, "No, it's not the same."
So you want to find out if it's the same question? So I forbid you to offer any consultation to the MSc students. And if you do offer any of such, and I forbid all the other PhD students to offer any consultation to the MSc students on this problem.
But what if they come for consultation?
No, they should go and try to think of the way. It's very simple. Don't worry. It's very simple. It's very simple, okay? Until you really try hard, don't just go because you feel probably they could know it, Try your own best, okay? Try to solve it. If you have some difficulty and something that really you tried hard to, get and you couldn't, then, like I said, even you can come to me. If you are in a dead end, you can come to me for probably a hint, because I will only give you a hint. I will not solve it for you. I can only give you a hint, okay? Because assignment is something that you are supposed to take home, try so that you digest, the material, and then try to apply it, okay? So more often than not, it's expected that you should do it. But in case you couldn't, or you need some hint or guidance on something, then okay, that is when you can go for consultation. Okay? And like I said, if you copy, then all right, I'm going to fetch the original and the copier. Okay? It is important that you do it independently. Of course, you can sit and rub minds. Okay? But not, okay, I finish. Okay, so just okay. Then I don't think you'll do this at this level. Now, let's move on. Vector representation of Darcy's law. I think calculation of horizontal components. VH, del L, del H by del S. Here, we said, what are the assumptions? Here we are referring to the horizontal components, okay? And the importance of referring to the horizontal components will become clear in the next few slides when we will be talking about transmissivity or transmissibility, okay? But here we have some assumptions in which we say that we have aligned anisotropy. And by that, we have minimum hydraulic conductivity in the vertical region. Okay? We have minimum hydraulic conductivity in the vertical region. And that's why here we are considering the horizontal component, because the horizontal components, it means we have only 2D, right? The XY plane. We are ignoring the vertical plane. Are you following? And we are ignoring the vertical plane because the hydraulic conductivity in the vertical direction is very small, about an order of magnitude less than that of the horizontal plane. Okay? But here we use a term called aligned anisotropy. What do you mean by that? I didn't ask you a question today, so I'll start with you. What do you mean by this aligned anisotropy? Yeah, aligned anisotropy. What is the implication? What do we mean? In practical terms, as it relates to hydraulic conductivity. What do you mean by aligned anisotropy? No, I didn't come to you. No, I didn't come to you. I'm specific now. Because I want everyone to be participating during the class. So it will not be fair for me to always be pointing at one person. Okay? Today I have asked you several questions, although I am not saying that I will not ask you any more, but let me now go around to some that did not participate in our class today. What do you mean by aligned anisotropy? Yes?
Sir, it's a condition where the aquifer properties are not the same at any given point.
Are not the same? Want to help him out?
That when the properties are not the same in all directions.
Yeah, you are defining anisotropy. You think this align has no meaning? You are just defining anisotropy. Which, I accept that when the aquifer properties are not the same at a particular point in all directions. That is anisotropy. But what do you mean by aligned anisotropy?
Uniform.
Huh? And let me tell you, I explained this yesterday very well, in clear terms. And all of you were here. All of you were here. I explained this in clear terms very well. Yesterday. What? Okay, you want to check your note? Do that. But I'm very sure that I explained this very well.
This will make me feel I don't know how the exam will look like.
Pardon?
I don't know how the exam will look like.
Exam will be like exams. Exams will be like exams. But now, are you thinking that probably I will just go and bring something completely outside, something that I know, I taught, I know that it was clearly understood, or what? Because this one, I took a lot of time yesterday explaining it. And even now, if I will say anything about it, you will, So it begs the question, are you really understanding what I'm teaching or no? Did you get my point? This particular thing yesterday, I explained it to the letter. Here. And all of you were here. But now it's appearing as if, it is something completely foreign. So if you move at this pace, definitely, even the exams, you will pick the exam question paper and say, no, this is wrong question. Wrong code. It doesn't belong to us. It belongs to maybe environmental or PhD or whatever it is. Am I right? At the pace at which we are moving, if you don't change, isn't it? Because I mentioned a lot of things now that I taught you before, but some of you couldn't remember at all, isn't it? So if we move at this pace, definitely when you pick the exam question, you say, no, this is the wrong code. Please bring the correct exams. This one I explained clearly yesterday. Took my time. Okay, try.
If the hydraulic conductivity along xy, where kxy is equal to ksx is equal to 0 in all directions.
What? Can you come back, please? Let me sit down. Yes, let me sit down first so that I can comprehend. Yes.
Kxy is the same as kyx. The 6 components, they are equal to 0.
He's trying to say the cross terms are equal to 0.
The cross terms are equal to 0. I agree with you. Yes, that is it. But why do we say align? What is the meaning of that align as it affects the hydraulic conductivity? I agree with you, yes, it's when the cross terms are 0. Granted. What?
When they are 0 horizontally.
No, they are 0. I accept. Horizontally, they are orthogonal. So you cannot just say horizontally. But why do we say align?
The anisotropy is directed, specified.
What?
The anisotropy of the conductivity is specified.
What do you mean by specified?
It's having a directed property.
Can someone panel beat and fine tune what he's trying to say?
Because they are symmetric.
No.
I think when the cross terms are equal to 0 and the principal terms equals to k, that's kxx,
No.
kxy, kxz.
No. Because in that case, we'll be left with one single value, a scalar, not a tensor, or 0 rank scalar. Anisotropy in that case is no longer there, isn't it? When you have kx, equal kx is equal kyy equal kz equal one value, then there is no anisotropy, isn't it? You can check your note. Don't worry, open your note. It's not in your note. Why?
We only ask.
You must learn how to take notes. That's very important. You must learn how to take, and this I have been emphasizing in every class, even today, isn't it? When I was telling you about the IQFA, the confined, my explanation, I said you must learn to take notes. And I'm not moving very fast. I wait until you get the concept clear before I move on, isn't it? On one slide we can spend 30 minutes explaining it. So I don't rush you. I wait until the concept is very clear before I move on. But unfortunately, when I come back, maybe the next class, and I ask you about pertaining something that I took time to explain, you will all appear as if I am speaking in another language. And when you open your notes, you cannot see anything because you didn't take down the note properly. I told you times without number. Should I mention anything new to you, or even if it is not new, because some of these things are more or less like revision. They are things you did before. So you can just put them down, and most especially something that is new. It means you need to clearly spell it out. And this, I took my time yesterday to explain it very well. Yes, let me come to you.
Aligned anisotropy.
Yes.
When equals time not equal. That's when kxy is not equal to kyx.
No. I accepted his definition that the cross terms are zero. So that your definition now is ruled out. Yes.
You see here, when the coordinates of each of the axes, let's say each of the planes are aligned with the principal axis.
No, it's the other way around. When the principal directions are aligned with the coordinates, with the Cartesian coordinate system. Didn't I mention this yesterday? Can you remember something like this yesterday? No, first of all, the most important thing is to understand. Even if you didn't write anything down, because like I said, we have different people here and we all have different ways by which, we assimilate. There are guys probably that may not jot down anything, but everything that is being mentioned will be retained. Did you get my point? So the most important thing, the first thing is you have to understand. And then, if you feel the need, then you put it down in your own words, in your own language, in whatever way that when you pick it, you will understand, okay, this is what it means. I mentioned that you have principal axis, which is kxx, kx, kyy, and kzz, isn't it? When these principal directions are aligned with the coordinate axis, which is the right-hand rule, using the right-hand rule, this is the right-hand rule for our 3D, isn't it? This is y, x, and z. So when the principal directions are aligned with the coordinate or the Cartesian coordinate system, we say we have aligned anisotropy because they are aligned. So that's why I was asking him to tell me, what do you mean by aligned? Because the word aligned is not just there for nothing. Are you following? Because when they are aligned, it means the other cross terms will not have components along the principal directions because they are all orthogonal. They are 90 degrees, isn't it? So they will all cancel out. They will become zero. So that's why I accepted his definition that yes, when we say aligned anisotropy, the cross terms are zero. But, what is the meaning of that aligned? Yeah, it's aligned because the principal directions are aligned with the coordinate axis. Because that is what will now make the cross terms to become zero. Are you following? And yet, we will have 3 values for the hydraulic conductivity, not 1. We will have kxx, kyy, and kzz. Is it clear now? Pardon? Ah. No, it's not about coming again, but do you understand it? That's the you can write it down in whatever way you feel like. But the most important thing is to understand it. So that during our next class, when I mention aligned anisotropy, the concept will quickly come back to you. Okay, for aligned anisotropy, the principal directions, which are the kxx, kyy, kzz, are aligned with the coordinate axis. And for that, you have the cross terms to be 0. This, I drew the box and then explain this and then explain when they are aligned, all this cancel out, isn't it? But probably while I was talking, you were listening and you understood, but then, I don't know, maybe your mind, your physical body is here, but your mind probably is wandering about. And fortunately, the class is held in the morning. When your brain is fresh, no disturbance, nothing, you just woke up from sleep and then walk down to the class. So, aligned anisotropy. We have minimum hydraulic conductivity, Kz, which is vertical. And a reasonable assumption, this is reasonable assumption for horizontally layered or fractured aquifers, because, like I mentioned, the horizontal hydraulic conductivity is greater than the vertical by an order of magnitude. This is, when we say order of magnitude, we mean one complete log cycle. When we say one log cycle, we mean 10, isn't it? 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. That's what we mean by order of magnitude. When we say something is greater or lower by an order of magnitude, we mean 10 times. If we say 2 orders at least, or we say several orders of magnitude, it means 10 to the power of, let's say, n, where n it could be 5, it could be 10, just to demonstrate the relative size, or comparing 2 quantities, their relative sizes. So that is what we normally use. Okay? For horizontal isotropy, horizontally, because if you look at this, although this is not for the K, okay, you have horizontal and then you have the vertical. The vertical, because it's small, we are neglecting it, but horizontally we are considering isotropic case. By isotropic case, we are saying that Kx equal Ky equal Kh, meaning we have 2 different conditions. Okay, for the complete system, we are saying that we have aligned anisotropy. Okay, and we are neglecting Kz. But horizontally also, we are saying here we have horizontal isotropy. Because horizontally, we still have 2 values of K, Kx and Ky. So we are saying they are the same. Okay, because they don't differ much. Okay, but they differ greatly when you compare them with the vertical component. And the vertical anisotropy is typically much greater than the horizontal anisotropy. Exactly what I mentioned in different words. Now, calculation of vertical components of Vz and Qz. Okay, Vz, this is Qz. Now, using subscript or indicial notation, let's take some break, okay, for some few minutes, and then we'll come back. These are different notations that we use in expressing our quantities in compact form. The first one we have seen was using the vector, isn't it? The same thing we express using the vector. And this is a tensor, isn't it? Okay. This is a vector. Am I right? This is the compact form. This is another way of expressing the same thing, using what is called indicial or subscript notation. Because as we move on, we'll be using both. We'll be using the compact vector form or the indicial or subscript notation. And we need to understand each one of them. And also different texts could use all of them or could choose to use either the indicial or subscript notation or the vector form. Okay? So let's take a break. After some few minutes, we'll come back and then we move on. I'm hoping to finish with these slides today. Okay? Yes.
What you sent yesterday is invalid.
Pardon?
What you sent to the group chat yesterday is invalid.
What do you mean by invalid?
It's not downloadable.
It's not downloadable? Yes. At all?
I click on it several days. It's still saying the same thing.
Okay. Then I will give the direct link to where to the direct link on the website so that you can download, because that is, I refer that to my copy in my Dropbox. Okay, so I will now get the link online and then post it so that once you click, it will just start downloading. Okay. Right. We are back from the short break. Now let's explain this subscript and indicial notation. Okay. This is Qi equals Kij, J subscript small j, isn't it? And here we said where the subscript I and j indicate xj and xi and xj respectively, with x1 equal x, x2 equal y, and x3 equals z. Although the hydraulic conductivity tensor at a point within an anisotropic porous medium is independent of the coordinate system used. I told you we have many coordinate systems: the Cartesian coordinate system, cylindrical coordinate system, polar, Euclidean, and a lot of them, isn't it? So it's independent. The tensor, the hydraulic conductivity tensor at a point, is independent of the coordinate system used, but the magnitude of each of the components depends on the chosen coordinate system. And you have seen that, because that's what takes us to even alignment or not alignment, isn't it? Aligned anisotropy or unaligned, isn't it? If it is aligned, then the cross terms will be 0, isn't it? For mutually orthogonal directions in space, chosen as the principal directions of coordinate system for expressing the components of K. So this is exactly what I'm saying. When the principal directions are aligned with the coordinate system, so in this case, you have Kij equals 0 for all i's not equal j, meaning the cross terms, isn't it? Because when I equals j, you have the principal directions, isn't it? Kxx, kyy. Okay? And it is not 0 when I equal j. But for cross terms, that is when I not equal j. When you have xy, yz, zy, zx. Okay? This is in terms of x and y. We can use numbers. Like now, let's look at this. Can we try to expand this using matrices? Because all these can be expressed using matrices. Okay? We can just look at them and expand them, because I and j all varies from 1 to 3. But how do we expand? Just using the indices, like this one. We start with I equal 1 and what? J equals what? 1. Okay. What do we have? We will have Q1. Am I right? Q1 equals what? K11, J1, isn't it? Plus what? Plus, you will have to take j throughout its values when I equals 1. Okay? Plus, I still is 1, but j will increase to 2 and 2 plus k, j what? Now, when we take the next one, I equals 2. J also has to start from 1 to 3. You take it all through. So, in this case, we will have Q2, right? Which will be equal to K? 2, 1, J1. J1. Plus what? K? 2, 2. Because I is pegged at 2. J will take it throughout 1 to 3. J2 plus K 2, 3, J3. The same thing when we have Q3. Okay? And this will be what? K 31 J1 plus what? 32 plus what? J what? If you look at all this, when x equal 1, this is just x1, isn't it? Qx, isn't it? Or Qx when x equal 1. For 2, this is just what? Qy. For 3, this is just what? Qz. Am I right? This is the expansion of the initial form. And then the same thing, because all these are matrices, because this is also simplified to this form. Because J is del minus del H over del Xj. So the same thing here. When we're expanding using this, so when J equals 1, we use del X. When J equals 2, we use del Y. When J equals 3, we use del Z. As we wrote it, X1 equals X, X2 equals Y, and X3 equals Z. So, using the same thing, we can still express this because Q is a vector, right? So, we have Qx we have Qx, Qy, and Qz, isn't it? And then this is equal to, that is a 3 by 3 matrix, isn't it? Kij, okay? Which is, if you want to make it in 1, 1 or whatever, this is 1, 1, 1, 2, isn't it? 1, 3. Am I right? Yes. This is 2, 1, 2, 2, and 2, 3. This is 3, 1, 3, 2, and 3, 3. Oh, today I will enter into my... And then the other one, what is J? J1, J2, J3. So it's simply like multiplying this out. Am I right? For Qx, or you can call it Q1, Q2, Q3. For Q1, it will just be this times this. This times that, plus this times this, plus this times, isn't it? That's exactly what we had. The same thing, Q2 is equal to this times that. Q3 will be equal to this times that. Are you following? This is the simple expansion, okay? That we can do either using the initial notation or the matrix form, okay? In which case, if we have aligned anisotropy, we have this to be 0, right? This to be 0. So when we expand, we will have terms in only K11, K22, and K33. Are you following? Yes. Okay? And this, I think, is something very simple. Can I clean this? This one? Okay. Now let's move on. Generalization of Darcy's law to 3D. Here we have anisotropic hydraulic conductivity, and the anisotropy aligned with coordinate axis. So now that is clearly captured, right? 3 vector components. Oh, these are just the ones that I erased now, isn't it? Qx, Qy, Qz, isn't it? And then this is the volumetric flux, okay, in vector form. This is the hydraulic conductivity for aligned anisotropy, isn't it? So all the cross terms are 0, and this is the hydraulic gradient, the gradient, okay? This is a vector, a tensor, and another vector, this is now the shorthand representation. And from here, we can expand this. You can be given this to expand, isn't it? Because this is a tensor, isn't it? This is a vector, this is a vector. You just transform it back to this one, isn't it? Depending on whether it is aligned or unaligned. If it is unaligned, then you will have value, you will have your cross terms. And then you use your knowledge of matrices to just multiply them out to get what is Qx, Qy, and Qz in terms of Ks and the gradient. Are you following? I think this is something which is similar to what we worked out now, isn't it? Okay? And if asked to expand this, you can go revert to the matrix form and then take the matrix multiplication, right? Here we have the 3D velocity calculation, where we divide the flux by porosity, which is a scalar, and the vector has three components, as usual, okay? Vx, Vy, and Vz. And we have also explained the significance of each of these components, isn't it? That the flow is usually horizontal, okay? And the vertical component is usually neglected because the value is so small, or sometimes it doesn't even exist. Although we are going to expatiate more on that, I think, in the next slide when discussing about the transmissivity. And then this is the vector form. This is the velocity vector. This is the hydraulic conductivity, okay? This is the hydraulic, the gradient, and then this is 1 over n, okay? And in compact form, or the shorthand representation, you can simply write it this way, okay? Minus k dot this dot that. Also, this dot here is not signifying dot product, okay? Because tensor is not a vector, okay? The only vector here we have is the gradient, okay? So it's just simple multiplication. But of course, this is second rank tensor, isn't it? So it has 9 values. It's something that you can transform to matrix and then carry out some operation, okay? Now, moving a step forward, we have the transmissivity, okay? What did we define the hydraulic conductivity? I mean, just as in hydraulic conductivity. With the ease with which water passes through the porous medium, isn't it? Now, we made mention about, we discussed a lot about the hydraulic conductivity, where we mentioned that it has 3 components, isn't it? But more often than not, we said in the previous slides, we neglect the vertical component, isn't it? Because its value is very, very small compared to the horizontal component. Okay? So its value is very, very small compared to the horizontal component. Here, when we talk about the flux, we'll talk about the flow now. The discharge. The discharge is given by, okay, let me say K, A, J. Am I right? K, A, J, isn't it? And then this area is the perpendicular to the flow path, is the area perpendicular to the flow path, isn't it? Which, when we have a saturated or confined aquifer, the cross-sectional area will be given by the breadth or the thickness, the aquifer thickness, isn't it? Times the width, isn't it? That will give us the cross-sectional area. The aquifer thickness times the width. If you remember, when discussing about the properties of the confined aquifer, we made mention of the fact that the aquifer thickness is usually very small compared to the length, its areal extent. Its length is usually several orders of magnitude greater than the thickness. Okay? So, for that reason, instead of being interested in the area, in the cross-sectional area, of course, we'll be interested in the cross-sectional area if the breadth, if the length and the thickness of the aquifer are comparable. If the thickness of the aquifer and the length are comparable, let's say 50 meters and 50 meters, so in that case, we could have some vertical movement, some vertical flow, or some vertical component of the hydraulic gradient, or the flow, we can have some velocity in the vertical direction. That is when the thickness is comparable with the length. But when the thickness is uncomparable with the length, then the flow becomes largely horizontal. Are you following? When the thickness is uncomparable with the length, the flow becomes largely horizontal. That is in layman's language, but in technical language we will say that the horizontal component, the vertical component of the velocity is now neglected. Okay? The vertical component of the velocity is now neglected because the flow will become largely horizontal. When the flow becomes largely horizontal, we will not really be interested. Our interest shifts from the flow, because the flux is the flow, the discharge per unit area, isn't it? That's the flux, isn't it? The discharge per unit area. Instead, will be more or less because this is Q over BW. Our interest will shift to Q over A. It will now become Q this over W. The flux per unit width. Or specifically will be interested in the discharge per unit width, which is Q over W. This width, W, is a line segment perpendicular to the flow path, because this is a vector. The flow per unit width, this is also a vector, isn't it? This is not a vector. And this, yesterday, I took a lot of time to explain why it is not a vector, why the flux is a vector and the discharge is not. The same thing, because it refers to a particular area that is perpendicular to the flow path. The same thing with the discharge per unit width or the flux per unit width. The discharge per unit width, the width we are referring to is any line segment across the path of flow, which is perpendicular to the flow path. It is what? Perpendicular to the flow path. And when we take this ratio, what are we going to be left with from here? We'll have Q over W being equal to KBJ, isn't it? Am I right? W has been removed. Flow per the discharge per unit width, or for 1 meter of the thickness of the width, because the thickness is B. Now, what we are left with is KB. And this product, KB, determines how the aquifer transmits the water through the entire thickness of the aquifer. Because this is B, the thickness. K is the ease with which water flows through the void spaces. While the term, the product, KB, it determines how the aquifer transmits the water throughout its entire thickness. And that is what is called transmissivity. T. Are you following? That is what is called transmissivity. T, or transmissibility. You call it transmissivity or transmissibility. And definitely, because this is a second rank tensor, this is also a second rank tensor. Are you following? But it determines, it gives the ability of the aquifer to transmit water throughout its entire thickness.
I was following till that stage. I didn't know how you get KB with this solution.
It is just from here. Did you follow up to this? A is what? BW, right? When I take the W down, Q over W, what am I left with? KBJ, right? Are you following now? Okay. So, now, but this holds true. I mean, this is applicable when we have 2D flow, isn't it? When we neglect the vertical component of the velocity, isn't it? Or of the flow. When the vertical component is neglected. And when do we neglect the vertical component of the velocity?
It's too small.
When?
It is too small.
What is too small?
The thickness. The width, the thickness compared with the length.
The length is several orders of magnitude greater than the thickness, isn't it? In that case, it becomes largely horizontal. And that is where transmissivity comes in. And that is where it can be used only when you have, or when the flow is 2D. Not only 2D, but in the XY plane. Because when we say 2D, it can be YZ, isn't it? When you don't have flow in the vertical component, that is where you can use the concept of transmissivity. Are you following? So, transmissivity simply, it is a function of xy, which can simply be defined, let's say from 0 to b, of the hydraulic conductivity, which is x, y, z. We can consider all the components for the hydraulic conductivity, but the vertical flow, because this hydraulic conductivity, not velocity. Are you following? And then this dz. So you are integrating throughout the thickness. Can you see that? From 0 to b. So you are like finding the flow, okay, throughout the thickness. So there will be no term in z. And that's why here I put, it's a function of x and y only. That is very important. And if you check most of the text, probably you will not find this explanation. But here, it has a significant role to play in groundwater modeling. Are you following? They'll just say, okay, transmissivity is equal to KB, and that's it. And then the unit from KB, K is LT, B is L. So it's going to be L square T. Usually expressed in meter square per day. But this is the, important explanation behind transmissivity. It is a concept that is considering only flow in the horizontal plane, not in the vertical plane. Okay, then what happens when you have partially penetrating well? Partially, can I clean this?
Yes.
When you have partially penetrating well, this is the ground surface, this is the water table, and then this is the confined aquifer. You have a partially penetrating well. What is the flow pattern around the bottom of the well? Is it horizontal or vertical? That's what I want to know. Partially penetrating well. Is it horizontal or vertical? Some will be horizontal, some will be vertical. Can you see that? Are you following? Okay, so this is the flow pattern. So when you have a partially penetrating well around the vicinity of the bottom or of the well, the flow is not purely horizontal. Okay? You have a lot of vertical components of the flow in that case. So this concept of transmissivity fails when you have a partially penetrating well. As we are going to see probably at the end, because we would like to take, let's say, mud flow, and model a particular groundwater scenario where you have sources and sinks here and there. And at the same time, you had me just mentioning something called sources and sinks. Right? Sources, as the name implies, they add, isn't it? They are adding something. They are adding probably flow, they are bringing something to our domain of interest. Sinks, they are taking out. When you have a test well, a pumping test, you are taking water out. That is a sink, isn't it? When you have recharge well, you are adding to the domain, isn't it? That is a source. Are you following? These are very important terms when it comes to modeling, any modeling. Sources and sinks, because they are what we use to, change the particular problem to suit our own case, our own peculiar cases. by introducing sources and sinks. A source in a governing equation will be plus. A sink will be minus because it is taken out from the system. Because more often than not, when deriving the governing equation, we use mass balance. Oh, my time is already, you didn't alert me that my time is over. So, we use mass balance. We use mass balance to generate our governing equations. So, when you add another mass, it is plus. When you take out any mass, any given mass from the system, it is minus. Okay? But this will expatiate more when we come to the derivation of the governing equation of groundwater flow. Okay? But near sources and sinks, like this one, the partially penetrating well, you can be pumping into the well as recharge well, or you can be taking out of the well. Near sources and sinks, the flow is not largely horizontal. You have vertical flows there. Okay? Now, so now we represent, in some text, this is the velocity, T dot del H, but divided by NB. Okay? Which is just another way of expressing this. Oh, okay. I cleaned it. Because the velocity is initially what? K over N del H, isn't it? Or minus K over N del H. Okay? So, and now K is equal to what? T over B. Right? T divided by B. And here you have NE. Some texts use it to designate or to denote effective porosity. Okay? So have you seen this equation somewhere? U of T dot del H hydrology. But you see, this is divided by NEB. Now, still on the transmissivity, you see, this 100 meters, you see 10 meters, 100, like that. So, very large aerial extent. Okay? The length is so huge compared to the thickness. For horizontal groundwater flow, common characteristics of aquifers and resulting assumption. Aquifers tend to be much more extensive in the horizontal direction than in the vertical. Because like I said, you have aquifers traversing countries. We may have an aquifer here that probably extends from here to Niger, or even beyond. And that is why, although probably we may not do that, there will be like, for transboundary aquifer, we must have a sharing formula. Because just like, in Nigeria, we know the oil we have, that is what they call, what is this formula? It's no. The formula with which the oil producing states.
Sharing formula.
Is it sharing formula? There is a specific name too. What? Derivation formula or what?
I think derivation formula.
Okay, it has something with which I think they are allocated 13%, isn't it? Also, of the. So the same thing, when you have transboundary aquifer, let's say aquifer traversing from here to Niger, because it crosses two countries, isn't it? So, what will be the rate at which Niger Republic can pump from that aquifer? And what will be the rate at which Nigeria can pump from the same aquifer?
We have to decide that something on this one.
We have it because so that like now Nigeria will not just wake up one day and make the aquifer go dry. It will not. It will be in such a way that it will be a function of some variables. There is a formula, a sharing formula to that effect, and that sharing formula takes effect one of the population density. Two of the area, like the aquifer, is it like 70% in Niger, 30% here, or the other way around? But what I'm saying is that there is a sharing formula, but probably, I don't know if we will discuss that later, but there is a sharing formula by which will dictate that, okay, Nigeria could pump up to this rate, and Niger could pump from this aquifer up to that rate per annum. And any violation is punishable.
Well, how do we identify the boundary? How do we identify that?
No, I don't know. Probably you will need to go to geology and I wanted to do that, but unfortunately up till now I didn't. I don't know, I was thinking probably we will have our aquifers mapped out.
Okay.
And I'm sure some of them are clearly mapped out with their depths, with their distances and what have you. And more so because we are all producing states. So even if we don't want to use it for water exploration, we can have it mapped out for oil exploration. And now that it is like cutting across all the country. Initially, we have oil only in the south-south. Now we have it in the southwest. And now we have it in the north. And by north, I mean from the north central to the northwest to the northeast. All we have, different exploration or different investigation taking place at different levels. So that will force, the explorers or the government into mapping or getting geological investigation of these substrata, of this geologic formation, their extent, the amount of water it contains, and what have you. Okay? But I am thinking probably geology will have some kind of compendium or some data with respect to that. Okay? And Niger also now, it has oil. So definitely it must have done all this geologic investigation before oil was spotted and then explored. So we have transboundary aquifers. Okay?
Sorry, sir. You say so that Nigeria will not dry out the aquifer.
Yeah, will not be pumping at a rate that it will be disastrous to the aquifer.
And my question is, during the first contact,
Yeah.
you made mention of the percentage of groundwater level, where we are talking about the sustainability, comparing the surface and the groundwater.
Yeah.
You say groundwater cannot be exhausted.
No, but I made a lot of comments there, isn't it?
Okay.
I didn't just leave it open. It was not an open statement. If you remember, I clearly mentioned that, confined aquifers are under pressure, isn't it? And that's why they have piezometric surface. Okay? They are under pressure. But every confined aquifer has a source, an outcrop, where it receives recharge. Okay? It has a source where it receives recharge. Unless if we are talking about, I made mention about an aquifer or fossil water. Remember?
Yeah, you said something.
Yes, I said a lot about fossil water, which is water that was deposited for time immemorial, for a long time, just like we have oil. As a result of decaying natural organic materials, this and that, over time being changed due to variation in pressure, this and that, and then oil was formed, isn't it? The same thing, deeper down, we have fossil water, which resulted from different infiltration, recharge, and what have you. And still, because pumping from any aquifer, I said what? Affects the quality. So I just mentioned drying up for the sake of, explaining the fact that it has a particular impact on the aquifer. Yes, of course. The rate, it could affect the quality, salinity could increase drastically, the quality of the water could drop drastically, and all these are things that we don't want to happen to our aquifer. But drying up, as in drying up, that may be far from our context. Okay? Because the amount of water is so huge that exhausting it per se is not something we envisage. Okay? All right. So aquifers tend to be more extensive, and hydraulic conductivity tends to be higher in the horizontal direction. Okay? It tends to be higher in the horizontal direction. Although here, you see, we consider the vertical component. So even here, we may choose to neglect it. But T is strictly a function of X and Y. That's very important. Strictly a function of X and Y. Thus, the vertical flow is often neglected, which is what is called the Dupuit assumption. This allows the use of transmissivity as a measure of the aquifer's ability to transmit water throughout the entire thickness of the aquifer. Okay? And then we can change it into this. Instead of KHB, because here we are using only X as a function of X and Y, isn't it? So this will now become T. And then 2D Darcy's law, flow per unit width of the aquifer, which is flow per unit width, becomes this. Okay? And then this is the example where we have a partially penetrating well. What about if we have a fully penetrating well? What? The flow is lateral. Horizontal. Because lateral is something else. Isn't it? The flow will be pure because if you have a fully penetrating well, meaning it penetrates to the bottom. So it will just be horizontal. Okay, in that case. Close to a source or sink, the flow may have significant vertical components, while away from the source or sink, the vertical flow components may be negligible. Okay? Note that just under each partially penetrating well, the flow is surely vertical, as we can see under it, isn't it? It is surely vertical. When the well is fully penetrating the well, there exists no zone with vertical flow components. Then, here we have 2D and 3D mode, isn't it? In 3D mode, this mode is recommended when the vertical and horizontal dimensions of the considered domain are comparable, isn't it? This I mentioned. When the vertical and horizontal dimensions are comparable, Darcy's law deals with the specific discharge. Here we use flow per unit area, isn't it? But in the 2D mode, this is applicable when the domain's thickness in the vertical direction is much smaller than its horizontal extent. And in this case, we need an expression for the discharge per unit width rather than per unit area throughout the entire thickness of the aquifer. And then we use Q prime of x, a function of x and y. Here width is a line segment in the plane, and the discharge is normal to the line segment. I think this I already explained each of these terms. And then Txy is equal to this. Okay? Oh, we'll take this concept quiz next class. It will be the first thing to take. And then these are some references which will be good for you if you can consult them. Then in the next class, we'll take the concept quiz and then move on. Okay?
I think you post the material before the next class.
This one? Yeah, I'll post it. I'll post it today, okay? Any question? So from next week, our classes will be held for a period of 3 hours, okay? Thursday and Friday, 3 hours, so that we can quickly round up. And at this stage, we have really gone far, although if you look at probably the number of slides we did, they are very small. I mean, the number is not much, but what we have said and what we did is really a lot, okay? So make sure you understood exactly what we did before. If you think that we haven't done much, we just have 2-3 slides, presentations here and there. No, we did a lot of things. Okay? So make sure all that we did before is very clear to you. Okay? And then we will move on.
Sir,
yes.
In this slide, in which place the modeling aspect is?
Throughout, from the beginning till the end. From the beginning till the end. What is the modeling aspect? Let me ask you this. What is the modeling aspect? Huh? No, I'm asking you, what is the modeling aspect? What do you understand to be the modeling aspect?
Modeling is the knowing of equation to predict particular results.
To predict what?
Outcome.
To predict outcome. Okay. So here you don't see any equation that can be used to predict anything. Yeah. From here, probably, the next thing we might do is to derive the flow equation. And when we do that, you realize it is in terms of the transmissivity, storativity, pressure head, hydraulic conductivity. But then all this, 3D discretization that we did will now become very important. And then all we need to do is to get a code that can solve that equation Once it is solved, because it will give us the value of the head, isn't it? Based on certain scenarios. All we need to get is the value of the heads, the pressure heads. And then we use the pressure head in the Darcy's equation to get the flow velocity. And then that's it. But you need to understand all this. All that we did from the beginning of this slide, they are also the modeling processes. Okay? But like I said, I will not just come and write the governing equation. Okay. Our governing equation is del square H equals 0. If that is what you want us to do, no, we don't start like that. We'll start gradually. We move up. Okay? Up to where we will reach this point. And then once you understand all this, the motion equation, the Darcy's law, the different parameters, then it will become easier to understand the modeling results. Okay? But without this background, you will not comprehend anything. Are you following? So all that we did right from day one, we have started the groundwater modeling proper. Okay? And don't underestimate anything that we did and think that, oh, no, this doesn't belong to the groundwater modeling. Don't do that. Everything we said, everything we did is part and parcel of the groundwater modeling. Okay? Any question? So, see you next week. But I will post the homework today.